Okay, this is physical chemistry. We're just starting chapter 12. We're in section 1, obviously. In this chapter, we're going to be talking about colligative properties. Colligative means bound together. The four colligative properties we're going to talk about: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Now, we're going to talk about all these in a lot of detail in this chapter, but for now, here's a quick introduction. Let's say we have some pure water, and then we're going to add some non-volatile solutes, such as sugar, to it. So we have pressure against temperature. Now these solid lines here, this is our phase diagram. I didn't show it, but this should be actually solid, liquid, gas. But anyway, so the dotted lines, this is what's going to happen after you add some solute. So, like I said, sugar, non-volatile solute. So what's going to happen, our temperature, our freezing temperature, the pure substance, is going to become temperature freezing. So we're going to change in the freezing point. And then our boiling point, pure, is going to become a higher boiling point. So this is our boiling point elevation. And then because of this, we're also going to have a lower pressure. So this is our vapor pressure depression. And then we can't show osmotic pressure on this diagram, but we will be talking about all four of these later anyway. Continuing on physical chemistry, chapter 12, we're finishing up section 1, the colligative properties. So if we add anything, a solute, to our solvent, in this previous example, water, H2O, it's going to make its chemical potential drop. That should be obvious because of this derivative here. The derivative of the chemical potential of A with respect to the mole fraction of A, holding temperature, pressure, and all other substances constant, has got to be greater than 0. Now we also remember this: chemical potential of A is equal to the chemical potential of A star at whatever temperature and pressure of interest, plus RT as the natural log of mole fraction of the A. Now, if you have pure solvent, like in our case water, mole fraction is going to be 1. But then if you add anything else, that mole fraction is going to be down. It's going to be less than 1. It's going to decrease. So if this number is going to decrease, then this number will be negative, even more negative. So this will drop. Okay, physical chemistry, chapter 12, we're in section 2 now. We're going to talk about vapor pressure lowering. Now, for now, we're going to assume that we have a non-volatile solute. So the solute can be either solid or liquid, but it'll have no vapor pressure. That's what non-volatile means. Now, glucose, just so you know, is C6H12O6, and sucrose is C12H22O11. We're going to be talking about sugars later on because, well, those are both non-volatile solutes. Anyway, so the pressure of the solution, therefore, is due to the solvent only. Now, we're also, for now, just to make things simpler, we're going to assume that the solute doesn't break into ions. So again, that's why we're using sugars as an example. So the pressure of the solution is just equal to the pressure of our solvent, and that's going to be equal to the gamma of the solvent times the mole fraction solvent times PA star. Remember, star means unmixed. And of course, so this formula is going to be for any solution as long as we have a non-volatile solute. And of course, A would be the solvent. Now remember, the activity of A is just equal to the activity coefficient of A times the mole fraction of A. So gamma of A, remember, that's the solvent activity coefficient. And gamma of A is going to be equal to 1 if you have a non-electrolyte. And we're not going to be talking about electrolytes anymore in this chapter. That was just chapter 10 for now. So to figure out the vapor pressure lowering, it's just going to be equal to the pressure of the solution minus the pressure of the unmixed A, the solvent. So that's going to be equal to the gamma of A times the mole fraction of A times the unmixed pressure of A minus the unmixed pressure of A. We can factor out the unmixed pressure of A, and that's going to just factor out gamma of A times mole fraction of A minus 1. So just getting out rid of these intermediate steps then, for delta P is equal to the gamma of A times the mole fraction of A minus 1, all of that times the unmixed pressure of A star. And remember, if you have an ideal or an ideally dilute solution, then your gamma of A is going to be equal to 1. This is Physical Chemistry, Chapter 12, Section 2. Now we're going to talk about, for an ideally dilute solution, so delta P, we have the mole fraction of A minus 1 times PA star. If you have two components then, with B being the solute, then mole fraction of A minus 1 is just equal to minus the mole fraction of B. So we get delta P is equal to minus the mole fraction of B PA star. Mole fraction is positive, pressure is positive, therefore the change in pressure will be negative. That's why it's vapor pressure depression. Vapor depression. So anyway, so here's a graph of temperature versus the change in pressure versus mole fraction. This is in torr, that's kind of arbitrary because I didn't even put units. But we're actually talking about an ideally dilute solution here. So this is actually like less than 10% here. So for an ideally dilute solution, as you add mole fraction, the change in pressure, we're going to get lower and lower, or bigger and bigger change in pressure. Oh, that's backwards. Hang on a second. Okay, this is Physical Chemistry, Chapter 12.2. This is for an ideally dilute solution. So we said before how if you have only two components, the mole fractions add up to 1. So if mole fraction we have of A minus 1, that's going to be the same as the negative of the mole fraction of B. So if we have an ideally dilute solution, we know that the change in pressure is going to be the mole fraction of A minus 1 times PA star. So we're going to use that and substitute it and say delta P is equal to minus mole fraction of B times PA star. Now remember, we're saying A is the solvent, so B is the solute, because we only have two components. Now, we got a graph of the change in pressure against mole fraction of B, the solute. So we're going to start out with 0 solute increasing, and the change in pressure is going to start out 0. Now the dotted line here, this is a straight line, this is for an ideally dilute solution, and its slope is minus PA star. On the other hand, a real solution is going to curve down like this. And this will be true of any solute. So what we learned here is that the departure from ideal here, this is not based on the nature of the identity. It's based on the quantity, the concentration of the solute particles, not their identity, just like we did with electrolytes. So our conclusion then, the change in pressure is independent of the nature of B, the solute, and it depends only on its mole fraction. In other words, the number of solute particles in the system, the solution. Now we're in Physical Chemistry, Chapter 12, beginning Section 3. We're going to talk about both freezing point depression and boiling point elevation in this section. So here's the graph, just like we did before, of the change in pressure with mole fraction. Notice it starts out with 0 change in pressure with 0 mole fraction of B. Remember, B is our solute. And then we have a straight line for an ideally dilute solution, and then a real solution is going to curve down and have even greater change in pressure. Now, so what this tells us is way up here, at really low concentrations, any real solution is going to behave like an ideally dilute solution. We're going to use this approximation later on. Now, also remember, all colligative properties, they depend on the quantity, not the nature of the solute particles. Now, remember the derivative of the Gibbs free energy, the molar Gibbs free energy of substance I with respect to temperature at constant pressure, that's equal to the derivative of the chemical potential of substance I with respect to temperature holding pressure constant. And that's equal to minus the entropy, the molar entropy of substance I. Remember, we get this, we have dG equals minus SdT plus VdP. We're holding constant P, so we just have dG equals minus SdT. And then you can just solve for minus S there. That's how you can show this. We're continuing Physical Chemistry, Chapter 12, and Section 3 still. trying to figure out boiling point elevation and freezing point depression, I think. So at the melting point, the chemical potential of the solid, unmixed of course, we're talking about pure substance for now, is equal to the chemical potential of the liquid of the pure substance. Now remember, TF star is the freezing point, which is the same as the melting point for a pure substance anyway. And at the boiling point, the chemical potential of the liquid on pure stuff is equal to the chemical potential of the gas of the pure substance. And of course, TB star, that's the boiling point. So here's a graph of chemical potential against temperature. You notice there's actually three different straight lines here. One is for the chemical potential of showing what a solid would do. One is for the chemical potential of what a liquid would do. And one is what the chemical potential of a gas would do. All three of these are straight lines, and for any one of them, the slope is going to be equal to minus s. Now, at the freezing point, like anywhere along this line, the chemical potential of the solid star is equal to the chemical potential of the liquid star. Star means unmixed. And same thing for, oh no, wait a minute, not the whole line, this point right here. At this point right here is where the two are equal because the lines intersect. And then this point here, this is where the two lines for liquid and gas intersect. So the chemical potential of the liquid star is equal to the chemical potential of the gas star. So this is your boiling point, this is your freezing point. So this is your temperature of freezing for the pure substance, this is your temperature of boiling for the pure substance. So all along this solid region though, this is where the chemical potential of the solid is the lowest of those three curves. And then in between here, the liquid region, this is where this line, the chemical potential for the liquid curve, is the lowest of the three. And then beyond this point, the chemical potential for the gas is least. So you're going to have whichever phase has the lowest chemical potential. Since it's lowest, the solid curve is lowest here, the substance is going to be solid here. Since the chemical potential for the liquid curve is lowest here, then you're going to have liquid here. And since the gas curve is lowest here, then if you're above this temperature, you're going to have gas. Now, as the temperature increases, you would expect more entropy. So what that's saying then is each of these slopes gets more negative than the other one. So it's a steeper slope. Okay, this is physical chemistry. We're in chapter 12, section 3 still. So here's a graph just like the one before. We have the chemical potential of A going up in that direction. We're talking about water still. And then we have increasing temperature this way. Now these solid lines, these are the pure water just like we had before. This is the solid region, the liquid region, the gas region. Then this dotted line, this is the chemical potential line of water as a solvent, but after we've added some solute. As you can see, it shifted the line this direction. Now we have not changed the slope of the line. We've simply shifted it a little bit. What that's done is it's moved this intersection from here to here. So this was our temperature of freezing for the pure substance. Now the temperature of freezing is over here. So we have delta F and it's negative. Likewise, we've moved our boiling temperature from here to here. And so we've got a change in the boiling point temperature, and this one will be positive. Now, like I just said, the freezing point, it moves left, that's why it's called depression. And the boiling point, it'll move right, that's called depression. Now, what a boiling point of elevation, or any of these colligative properties actually, is not caused by energy. It's going to happen even when delta H mixing equals 0. In fact, we know for an ideal solution, delta H mixing is equal to 0. Think of mixing inert gases. They're, generally speaking, going to mix. So, if it's not caused by energy, it must be caused by entropy. And it turns out all four colligative properties we're talking about are caused by entropy. They have nothing to do with energy. This is Physical Chemistry, Chapter 12. We're continuing in Section 3. So let's say we have a container, an open container. We have liquid H2O in it, and then but it's open, so we can have H2O vapor, gas. I didn't show that. So we're going to add a solute now. What that's going to do is it's going to increase the entropy in the solution. Since the entropy of the solution, I'm going to show you why, that's going to give each molecule in the solution, or at least for the water, less of a reason to escape into the gas phase. Now, remember the graph I showed you on the previous slide. Delta F, the freezing point depression, is usually a larger absolute value than the boiling point depression, because remember the slope of the lines. The solid curve is the least steep. It's actually the highest slope because it's the least negative, but you know how that double negative stuff works out. So remember the formula, mu A equals mu A star, that's unmixed, plus RT natural log of the mole fraction of A. Now, for the pure solvent, we had the mole fraction of A is equal to 1. But then after we add some solute, we get the mole fraction of A is less than 1. And of course, temperature has got to be greater than 0. It's an absolute scale. The natural log of XA is less, the mole fraction of A is less than 0. So what that means is that mu A is going to be less than mu A star, because this whole term is going to be negative. So we're going to be subtracting from the original chemical potential. And remember, this mu A star, this is constant as long as you're at a certain temperature. Now, let's say we have an ideally dilute solution. The partial molar enthalpy of A is just that equal to the molar enthalpy of A in the unmixed state. And likewise, the partial molar entropy of A is just the molar entropy of A in the unmixed state, plus RT, natural log of the mole fraction of A. Now we know, and then the partial molar of entropy of A is going to be greater than 0. So if you find the chemical potential here, the chemical potential, just use H minus Ts, or in this case partial molar entropy of A, minus the temperature times the partial molar enthalpy of A. Temperature is positive. The entropy is positive. This whole term is positive. So this is going to be negative. So when we add a solute, the chemical potential of our solvent is actually decreased. This is Physical Chemistry, Chapter 12. We're continuing Section 3. We're now going to derive the formula to find freezing point depression for a substance. Now, for now, we're going to assume that pure substance A freezes out, the solvent. For example, think of salt water. If you have in the ocean, it's salt water, but at the North Pole, when the water freezes, you get pure water freezing out. So this is actually a pretty reasonable assumption for what we're trying to do for now. So what that tells us is that the chemical potential of A in the solution has to be equal to the chemical potential of A in the solid for the pure substance. This is assuming we're at equilibrium, doing it reversibly, of course. So the chemical potential of A for the solution, that's going to be equal to the chemical potential of A in the standard state when it's liquid, plus RT natural log of the activity of A. We showed that before. Likewise, we know the standard state is equal to the pure substance for a salt solution, especially for the solvent when we're talking about ideal or ideally dilute. So mu A in the solution, the chemical potential of substance A in the solution, is going to be equal to the chemical potential of A in the liquid state, unmixed, pure liquid, plus RT, the natural log of the activity of A. And then, of course, remember we showed before that we defined the activity A of any substance I is equal to the activity coefficient of I times the mole fraction of I. And remember, for an ideal or ideally dilute solution, gamma is equal to 1. So what that gives us, we're going to have that the chemical potential of the pure A in the liquid state plus RT times the natural log of the activity of A is going to equal to the chemical potential of A in the solid state. And it's, well, pure A, of course. So we know this is going to be at a specific temperature, the freezing temperature, at a specific pressure. So we're going to write this as a function of temperature and pressure. So we have the chemical potential of substance A in the liquid form, unmixed, at the freezing point temperature in whatever pressure, plus R times the freezing point temperature times the natural log of the activity of our solvent, and that's equal to the chemical potential of A in the pure solid and at the freezing point and whatever pressure. And since we're talking about standard state, P is just going to be 1 atmosphere. So just solve for the natural log of the activity of A, and that's going to give us that the Gibbs free energy, molar, in the solid form at the freezing point temperature, and that's pure, of course, minus the Gibbs free energy molar in the liquid form at the same temperature, the freezing point temperature, divided by R times the freezing point temperature. Continuing on physical chemistry, chapter 12, section 3. So we're still talking about a pure solid freezing out of a solution, and A is our solvent that's freezing out. So it's solid liquid equilibrium here. The change in the Gibbs free energy of fusion then is just the molar Gibbs free energy of the substance A in the liquid state minus the molar Gibbs free energy of the substance A in the solid state. And the star means pure for both. Now remember the Gibbs equation, well, one of them anyway, we have the derivative of the derivative of Gibbs free energy with respect to temperature holding pressure constant is entropy. That would still be true even if it's in a pure state. So the derivative of the Gibbs free energy for the pure substance with respect to temperature holding pressure constant is equal to minus the entropy of the pure substance. Now, if those two are always equal to each other, then their changes must be equal to each other also. So that we can also say that the derivative of a change in molar Gibbs free energy with respect to temperature holding pressure constant is equal to a change in molar entropy minus a change in molar entropy. We're going to be using this to substitute in later in a bit. So we have from the equation before, we just substitute in that delta and we get the natural log of the activity of substance A is equal to minus the change delta of molar Gibbs free energy of substance A for fusion. So we're talking about a phase transition here. This is not multiplied, this just means at the freezing point temperature, because we're talking about equilibrium here. We're talking about the solid liquid equilibrium. And then divided by R, the gas constant, and divided by TF, the freezing point temperature. Now we're going to take the derivative of this with respect to the freezing point temperature using the product rule. So we have the derivative, a natural log of the activity of A with respect to temperature freezing. I didn't specify constant pressure. It probably should be constant pressure actually. But so remember the product rule, the derivative of the first times the second plus the derivative of the second times the first. So we're going to have the derivative with respect to freezing point temperature of the change in the Gibbs free energy of fusion molar of substance A at the freezing point temperature, just times 1 over RTF. And then plus the derivative of 1 over TF times delta molar Gibbs free energy of fusion of substance A at the freezing point temperature divided by R. Continuing on physical chemistry, chapter 12, section 3, we're going to find the derivative now with respect to the freezing point temperature of delta molar Gibbs free energy at a fusion, which means going from solid to liquid, remember, of substance A, that's our pure solvent, at the freezing point temperature. This isn't multiplied, this is just specifying that this is temperature dependent. And that's equal to minus the change in the entropy molar of also a fusion of substance A, also dependent on temperature. Now remember that this was from the Gibbs equation that we showed on the previous slide. Then the derivative with respect to TF of 1 over TF is just minus 1 over TF squared. Remember, TF is the freezing point temperature that we're looking at. So now using these two in the equation on the previous slide, we can see that the natural log, the derivative of the natural log of the activity of A with respect to temperature freezing, holding pressure constant, just like I said, that's equal to the change in the molar entropy of fusion. Why did I write, this should be TF here. Oops. All right, at the freezing point temperature, divided by RTF, plus the change in the Gibbs free energy, molar Gibbs free energy of fusion of substance A. Also, that is dependent on temperature. Divided by RTF squared, because of substituting that in. Now, taking this sum here, we're going to simplify it using a common denominator, and we're going to split delta G into H plus TdS. So now that gives us the same derivative natural log of the activity of substance A with respect to the freezing point temperature, holding pressure constant. That's going to be equal to the freezing point temperature times the change in the molar entropy of fusion for substance A, that's temperature dependent, plus the change in the molar enthalpy of fusion of substance A, that's also temperature dependent, I didn't bother to write it, minus the temperature of freezing times the change in entropy of the molar entropy of fusion of A. And that too is temperature dependent. All that divided by RTF squared. Notice that these two terms, they're opposite plus and minus, so they'll cancel out. So what we're left with is just the derivative of the natural log of the activity of substance A with respect to the freezing point temperature holding pressure constant. It's just the change in the enthalpy, the molar enthalpy of fusion of substance A, pure A, at the freezing point temperature, divided by R times the freezing point temperature squared. Continue on physical chemistry, chapter 12, section 3. So now we've got the derivative of natural log of the activity substance A with respect to the freezing point temperature holding pressure constant is equal to the change in the molar enthalpy of fusion for substance A at the freezing point temperature divided by R, the gas constant, times the freezing point temperature squared. Now you notice how similar that is to the Van 't Hoff equation we learned way back in chapter 6. Which is the derivative of the natural log of Kp naught with respect to T temperature is equal to the change in enthalpy naught, remember naught means standard state, divided by RT squared. So now what we're going to do, we want to take the integral of both sides from state 1 to state 2. Remember that's what the 1 and 2 means. We're not substituting in the number 1 for A or anything funny like that. So this is respect to freezing point temperature, of course. Probably should write that here. But anyway, so the integral from state 1 to state 2 of the derivative of the natural log of the activity of A equals the integral from state 1 to state 2 of the change in the molar enthalpy of fusion for substance A divided by RT squared with respect to freezing point temperature. Now, we're going to say state 1 is just pure A. So our temperature of freezing at state 1 is just the freezing point temperature star, which means unmixed. And the activity of A in state 1 is just going to be equal to 1 because it's pure. Then at state 2, we're just going to say that's any general state. And so the activity of A in state 2, we're just going to call that the activity of A. And then the freezing point temperature in state 2, we're just going to call that the freezing point temperature. So now we have the integral for that is, well, the integral of the derivative cancels out. So we have the natural log of the activity of A in state 2 divided by the activity of A in state 1. And that's equal to this integral from state 1 to state 2 of the change in the molar enthalpy of fusion of substance A at the freezing point temperature divided by RTF squared dF. Continuing on physical chemistry, chapter 12, this is section 3. So we have all these formulas with the temperature of fusion. That's just a dummy variable. We're going to just call it T from now on to save space. Now remember, the activity of A is equal to the activity coefficient of A times the mole fraction of A. Now for a two-component system, remember A is the solvent, B is the solute. The mole fraction of A is equal to 1 minus the mole fraction of B. Now this, of course, assumes that there's no dissociation of B, there's no association of B, and that B is not an electrolyte. So, again, we're pretty much talking about inert solutes, like sugar or something. So the natural log of the mole fraction of A times the activity coefficient of A is equal, we're going to split that up. So we've got the natural log of the mole fraction of A plus the natural log of gamma of A. And then we're going to substitute this in, so we get the natural log of 1 minus the mole fraction of B plus the natural log of gamma of A. Now we're going to expand this one right here using Taylor's series from Math 253. So natural log of y, about y equals 1, and we're going to just say y equals 1 minus x of b, or chi actually, mole fraction. So now, using Taylor series expansion, the natural log of y equals y minus 1 minus y minus 1 squared over 2 factorial plus y minus 1 cubed over 3 factorial minus y minus 1 to the 4th over 4 factorial, etc. forever. So substituting the back in for y and simplifying, we get the natural log of 1 minus the mole fraction of b is equal to minus the mole fraction of b minus the mole fraction of b squared over 2 factorial. Uh-oh. One of these should be a plus, I think. Oh, shoot. Let me get back on you. So, and then minus the mole fraction of b cubed over 3 factorial. Continuing on physical chemistry, chapter 12, we're still in section 3. So we showed how using the Taylor series, the natural log of 1 minus the mole fraction of b is equal to minus xb squared over 2 factorial minus xb cubed over 3 factorial. Yes, these are all minuses, and that goes forever. So this is only going to be true for an ideally dilute solution, though, where xb is much less than 1, because it's a Taylor series. It's really only true in a small range. So also, from statistical mechanical theory of solution, we're not going to derive this at all, but the natural log of gamma A is equal to a constant B2 times the mole fraction of B squared, plus another constant B3 times the mole fraction of B cubed, etc. And where these B coefficients, they're all functions of temperature and pressure. So going back to what we had before, then the natural log of the gamma of A times the chi of A, that's, remember, activity coefficient times mole fraction of A is our solvent. That's going to be just equal to minus xb, combining both of these, plus b2 minus 1/2 times xb squared, etc. Now, we're going to be, since we're talking about an ideally dilute solution, xb is really small. So obviously xb squared is even smaller. So what we're going to do is just ignore all these terms. So this simplifies to just the natural log of gamma of A chi A is equal to minus chi b. So this natural log of the activity coefficient of A times the mole fraction of A is equal to minus the mole fraction of B. So now continuing with that same integral we had before, then substituting this in, we get minus the mole fraction of B is equal to the integral from the freezing point unmixed to the freezing point of the change in molar enthalpy of fusion of substance A divided by RT squared with respect to T. And remember, the enthalpy is a function of temperature. Continuing in physical chemistry, chapter 12, we're in section 3 still. So we're going to assume that we're in a small range of temperature for our freezing point depression. So we're going to go ahead and assume that the change in enthalpy of fusion, molar enthalpy of fusion for substance A is constant. So we can pull the constants out of the integral. That gives us minus the mole fraction of B is equal to the change in molar enthalpy of fusion of A divided by R times the integral from the unmixed freezing point temperature to the final freezing point temperature of 1 over T squared dt. Remember, we showed we're going to replace just T with TF, or TF with T. So we're going to have minus the mole fraction of B is equal to the change in molar enthalpy of fusion of A divided by R times minus 1 over T evaluated from TF star to TF. So that just gives us delta H molar fusion of A divided by R times 1 over TF star minus 1 over TF. We want to just do a common denominator here. So that gives us minus the mole fraction of B is equal to the change in the molar enthalpy of fusion of substance A divided by R times TF minus TF star divided by TF times TF star. Now we're going to also assume that our final freezing point is pretty close to the original freezing point. Remember, star is unmixed. So TF star TF is roughly equal to TF star squared. We also know that the change in the freezing point temperature is just going to be the freezing point temperature minus the original freezing point temperature. And that's always going to be less than 0, because our colligative properties, remember, adding a solute causes freezing point depression in our solvent. So, substituting all that back in, we get the change, and solving for the change in freezing point temperature, we get the change in freezing point temperature is equal to minus the mole fraction of B, our solute, times R, the gas constant, times the original freezing point temperature unmixed of our solvent squared, divided by the molar enthalpy of fusion of our solvent. Continuing on physical chemistry, chapter 12, section 3. So we have the mole fraction of B, the solute, is equal to the number of moles of B divided by the number of moles of A plus the number of moles of B, because we're assuming a two-component system. Since the number of moles of B is much less than the number of moles of A, because we have an ideally dilute solution, we can basically ignore it on the bottom term and just say that the mole fraction of B is equal to the number of moles of B divided by the number of moles of A. So now we have the molality of substance B, the solute, is equal to the number of moles of B divided by the number of moles of A times the molar mass of A. So remember, lowercase m is molality, that's moles per kilogram. So we want to do capital M is the molar mass in kilograms per mole to get the units to work out. Because N and M, these are just both moles. So rearranging that for NB, we get the number of moles of substance B is equal to the molality of substance B times the number of moles of substance A times the molar mass of substance A. Then the mole fraction of B is equal to the molality of B times the number of moles of A times the molar mass of A divided by the number of moles of A. And that also gives us that XB is equal to the molality of B times the molar mass of A. So that's what we were looking for. The mole fraction of A is equal to the molality of B times the molar mass of A. And this is an approximation, though, based on that, but you get the idea. So we're going to substitute that back into the formula we found for the freezing point depression, and we get the change in the temperature of freezing is equal to minus the molality of B times the molar mass of A times the gas constant times the unmixed freezing temperature squared, that's freezing temperature of A, remember, our pure solvent, and divided by the molar enthalpy of fusion, again, of substance A. Now, on the entire right side here, we're keeping everything as constant. We have such a narrow range for assuming molar enthalpy is constant and so on. So the only variable over here is the concentration of B, the molality of B. So we're going to define this constant K sub F, that's lowercase k for constant. So our freezing point constant, that's going to be the molar mass of A times R times Tf squared divided by delta H molar of fusion of A. So everything on the right side except for that concentration. Continuing on physical chemistry, chapter 12, section 3, we're finishing up freezing point depression. So we defined the freezing point depression constant, Kf, as just the molar mass of the solvent times R times Tf squared, star, that's unmixed, divided by the molar enthalpy of fusion for the solvent. So, substituting that back in, we just have the change in freezing point temperature is equal to minus the freezing point depression constant times the molality of B. Now for water, the freezing point depression constant is going to be 18, oops, did I write that wrong? Anyway, times 10 to the minus 3 kilograms per mole times 8.314 joules per mole Kelvin times 273.15 Kelvin squared divided by 6,007 joules per mole. So that gives us 1.86 kilograms per mole. And this is only for water, though. Now, we could actually use this process to find the molecular weight of B, but it's not a very accurate way of doing it compared to, boiling or whatever. Continuing on physical chemistry, chapter 12, finally finishing up section 3. So if we had more than one solute, then we would just add them up. So we get the change in the freezing point is equal to minus Kf, remember this is for the solvent, and then times the sum of the molality of each of your solutes. So remember, that's why I is not equal to A here, because you're not going to add up your solvent. So this is only true for electrolytes, though. And remember, back in chapter 10, we talked about electrolytes. Obviously, that'll come out a little bit different, more complicated. So that's all we're doing for freezing point depression. Now, this is all we're going to do for boiling point elevation because it's the exact same math. So our conclusions are that delta TB, remember, lowercase b is boiling. So the change in boiling temperature is equal to another constant, the boiling constant, molal boiling constant, times the molality of B. Oops, this should be capital B here. And capital B, remember, is our solute. So the change in, remember, delta TB, the change in boiling temperature, is just going to be your boiling temperature of the solution minus the original boiling temperature of the pure solvent. So the change in the temperature of boiling is going to be much less than the temperature of freezing. So if you wanted to use one of these two to find the molecular weight or something, you would want to use it freezing rather than boiling.